Good morning, everyone. And my name is Chao, a postdoc from Aalborg University. And today I'm going to talk about the control and stability of Dfidsc-based wind turbine system. And this is an extension of last day's course by Dao. And I think that this presentation is based on the latest research of our group. So it's better to have some basic understanding of the Dfidsc model and control. It's better to follow the course. And I think that if you have any questions during this presentation, you can directly unmute yourself and ask the questions. I hope that you guys can acquire some advanced modeling and control knowledge of the Dfidsc systems after this course. And it would be wonderful that you can use it in your later research. And that's the meaning and the motivation of this course. Okay, so this is the outline of today's presentation. First, I will introduce the research background, namely why do we need to do the stability and analysis of the Dfidsc-based wind turbine systems. And then I will introduce some stability analysis methods. How can we assess the stability performance of the Dfidsc systems when it connected to WinGrid? And based on this analysis, we want to provide some stability enhancement methods of the Dfidsc AC systems. And in the fourth part, I will, from another perspective, we may consider to connect the Dfidsc to a DC grid, and it may introduce some new performance and characteristics, and we needed to find some new control strategies of this kind of system. And the last part is the conclusion. Okay, so first I will introduce the research background of this presentation. And we know that nowadays, especially in the last decade, a lot of stability issues of the Dfidsc-based wind farm has been reported in the worldwide. And you can see from the left upside figure is a conventional Dfidsc system connected to a series compensated WinGrid network. And the difference between the yesterday's course by Dao is that here we are not only considering the Dfidsc is connected to a, maybe I can use a pointer. So you can see here that this is the difference of the between yesterday's topology connection. Here we consider the series compensated network. We also call it as a WinGrid network because in the real applications, the Dfidsc-based wind farm is not connected to a strong grid. It will connected to the grid through maybe 100 kilometers line and even more longer. So in order to reduce the inductance of the line effects, we needed to add some compensation capacitor like here. So it will make the line characteristic more complicated. So this is a representation of the series compensated network, and some articles may also have some compensated networks. But in general, it will make the grid's impedance more complicated. So since there is a grid impedance, and the Dfidsc will also have some different kinds of impedance in the frequency domain. So there would be some interactions between these two impedances. And this is a real case waveform that is reported in the South Texas in 2009. You can see that the first is the current waveform and the second is the voltage waveform. We can see that there are 20 hertz in the currents, and this is a very obvious oscillation phenomenon, and it will cause the trip of the wind farm and will cause some cascaded failures of the system and may even cause the outage of this area. So it's unacceptable in the real case, and we need to avoid. And this is also the second case that is reported in the North China, we can see that there are some 6 to 8 Hz oscillations of the DFIG wind farm when it connected to a series compensated system. You can see that there are some capacitor here, which means that it's series compensated. So you can see that in the real cases of the wind farms connected to a WinGrid, especially for the DFIG based, there are some very common oscillations happen in this phenomena. So we can we need to analyze what's the reason cause this kind of oscillations, and this is the first part we are going to introduce. So here I'm going to talk about the stability analysis of the DFIG AC systems. And in these slides, I'm going to make an overview of the existing stability analysis methods. And I think that most researchers are based on the 3 analysis methods. First is the Emt simulation, is the electromagnetic transient simulation. Is maybe based on the Pscat or the MATLAB. You can get a very accurate result by the simulation, but the disadvantage is that it can't reflect the internal characteristic of the system, and it unable to provide the design methods for this system. And the second is a state space model. It is also very conventionally used in the conventional power system, and it's based on but the disadvantage is that all the specific information are necessary in the system, like each parameters of the controller, and the entire system needs to be reanalyzed when the system have any changes. Like if I add one more DFIG based wind farm to the system, so it need to reanalyze the whole system, and so it will make it more complicated and not easy to scalable. And then is these days it's very popular to use the impedance model. And the advantage of the impedance model is that it only need the impedance characteristic of the input output of each link, and it like a black box model. You didn't need to load the details of the parameters of each part. You can just get the impedance of the model by the analytical models, or sometimes you can use the simulation or experimental results. So since that the impedance model have this kind of advantage, in the later research and analysis, we are going to use the impedance model for the stability analysis of the DFIG AC system. And here I'm going to show the very basic DFIG connected to the WinGrid connection. This is the topology, and this is a DFIG, the slater side and this voltage side, and the voltage side is connected to a voltage side converter, and this is connected to a dislink capacitor, and then I think there is a grid side converter here, but for the grid side converter, it has been widely researched in other researches. So in this presentation, I'm only going to mainly focus on the RSC and side of the DFIG. And this part, I'm going to introduce how to model this kind of system. I think that a basic idea is that we can divide the system from several parts. First is the DFIG part, it's a generator part. We know that the equivalent of the DFIG in the synchronous DQ frame can be expressed as this circuit. This is the stator side voltage USDQ expressed in the synchronous DQ frame, and this is URDQ. And this is the stator current, and this is the stator resistance, stator leakage inductance, and this is the mutual inductance, water side leakage inductance, and water side resistance. And this is these two electron voltage source are caused by the transformation from the alpha beta frame to the DQ frame. So I think that we need to have a basic understanding of this equivalent circuit of the Dfig. And in order to make it more intuitive from the impedance model, because from the impedance model, we only focus on the characteristics of the input voltage and the output current. And so we change it from the to this transfer function form. We can see that there are some, it can be expressed as the transfer function, and this is the formula of each transfer functions. And the input is the USDQ and URDQ is the stator side voltage and rotor side voltage. And this is the output is the stator current. So based on this, we can get the stator current equation from the stator voltage and rotor voltage. And what does the impedance or admittance mean? Is admittance is the relationship between the stator current and the stator voltage. So we can get the admittance like this form. And it should be noted that since the current and voltage of the Dfig are symmetric in this form, so we can use a complex variable to make it more simplified, just in one equation without use in the matrix form. So here we can get that since it's symmetric, so if we want to change it from the DQ frame to the alpha beta frame, we can just make a frequency shift. This frequency shift is omega 1 is the fundamental frequency that is used for the transformation from the alpha beta frame to the DQ frame. So based on this, only we make the impedance model of a single Dfig, like just the generator. We can see that the single Dfig is a symmetric plant, which just shows the inductive and resistive characteristic in the high frequency. You can see that this dominates the main characteristic of the Dfig. So it's very simple. It's like have a resistor and inductance, and this is a coupling terms. Okay, so but in the real case, we can't only analyze the Dfig. It should be controlled by the RSC. So we need to control to consider also the RSC converter. So when the RSC converter is considered, but without considering the Park transformation and the inverse Park transformation, which is caused by the PL, without considering the PL effect, we just considering the closed loop control of the rotor current. We can see that we need to add current control. This is mainly a PI controller, and this delay effect to generate the rotor voltage. So we can see that this is the current controller. This is the delay effect by the sampling and the PWM part, and then we can get the current equation based on the stator voltage and the rotor current references, and still we can get the impedance admittance of this kind of control. Here we can see that is still a symmetric form, so we can just use a frequency shift to get this equation to get the admittance in the alpha beta frame, which can be analyzed as a SISO system. But when we need to consider the PL effect, so here we can see that when we considering the PL effect, it means that in the real cases, since the PC voltage is not a constant voltage, if you are considering the grid impedance, when you are injecting power to the grid side, so the PC voltage will have some variations and fluctuate with the power injection. So it will cause some effect to the acquired CWPL, and then the CWPL is used for the Park transformation and the inverse Park transformation for the current control. So it will indeed have some effect to the current control. And how to analyze the PL effect? So we need to make a small signal of this PL effect. And we need to have a better understanding of the PL effect is to know what does the PL really do during this process. We can see that for the PL part, the input is the stator voltage. Yes, you can see that US alpha and US beta is in the stationary frame. And then you need to make a Park transformation. It's like to use this exponential function to times this voltage. So you can get the QX voltage, and then you by throw a PI controller to control this QX voltage to 0 and to make the stator voltage vector to be aligned to the DX, since the QX voltage will be controlled to 0 in the steady state. Okay, so then we can get the CWPL. And this CWPL is used for the Park and the inverse Park transformation. And this is the transformation formula. And here we can see that you have 2 frames here. Without using the super subscript, it represents as a real frame. It means that in the real stationary frame or the rotation frame is in the system frame, like it's a real frame, also called as. And this is a control frame. Control frame means that we are doing the PI controller and some other controllers in this frame. We need to use it in the synchronous frame. So how can we get this frame is that we use these exponential functions and also called as the Park transformation in the matrix form. Okay, so since here we get this formulation, then we can get the small signal of the SRF PL. We can get the relationship between the perturbation of the stator voltage, and then we can get the variation of the angles, the CWPL. So we can see here that this is a scalar value. It means that the variation of the PL angle is only related to the QX voltage. It has no relationship with the DX voltage. That's the main reason caused the asymmetric characteristic of the PL effect. So we can see that the small signal of the RF PL is asymmetric. What is symmetric? What is asymmetric? Asymmetric means that it can't be simply represented by a complex variable form, because here we have the DX voltage and QX voltage. Since the stator CWPL is only related to the QX voltage, it means that you just related to the QX voltage is asymmetric, and the complex vector model can't be applied directly. So to make it one step forward, we need to analyze what this kind of variation of the CWPL will have on the Park transformation, on the current Park transformation and the inverse Park transformation. We can see that here, if we want to get the water current in the DQ frame, we need to use this Park transformation. And this Park transformation is based on the CWPL. And this CWPL is affected by the PC voltage, just as the one slide previous have shown. So it means that if we do a small signal linearization of this equation, we can get that in the control frame, that is also in the DQ frame, you have a variation, and it's not only related to the VO variation, it also have been introduced by the Park transformation with another term. Just I have marked it in the red forms. You can see it here. It introduced this term. So the difference with between the considering the PL and without considering PL is that do we consider these terms introduced by the Park transformation? Okay, so but we can derive the formula of this transformation that it is asymmetric matrix. You can see here that it's asymmetric, and for the inverse Park transformation is also asymmetric. So if here we encounter this asymmetric matrix in our modeling process, that means we can't use just one complex vector to express all the variables in our system. It means that the small signal model of the FPL is asymmetric and the complex vector model, so can't be applied directly. We need to find some other methods to model this whole system. So it means that since we can't use the symmetric complex vector form, so we need just to use to the matrix form. It means the matrix form. It means that we have to consider the 2x2 forms here. So when we are considering the PL effect, you can see that is the green block I have marked here. That we have added this term compared with this without considering the PL effect. And this is considering the PL effect. We needed to add these two terms in these equations. And most of these equations like G1 dq, G2 dq, and GC dq, and all these red block and the blue block inside are symmetric matrix. But once your system have the asymmetric matrix, it will make your whole system become asymmetric. So the complex variable simplification form can't be used directly. You need to consider this asymmetric matrix. So it will make your whole system asymmetric. It will make your transfer function from the USDQ to the ISDQ become a 2x2 matrix. So you can see here that this is a 2x2 matrix of the admittance. And since this is asymmetric due to the PL effect, so if we are considering the PL effect, it means that we can't use the SISO method. SISO means the single input and single output system, and we need to use the MM method. It means that we need to use to the for the multiple input and multiple output methods to analyze this kind of stability issues. And here I want to introduce a very important part about the relationship between different impedance models. I think that if you have some basic understanding of some basic experience of doing the impedance modeling in your previous research, maybe you have encountered these three different concepts like the DQ scalar impedance, DQ sequence impedance, and alpha beta sequence impedance. And here that's some scholars that may prefer use the sequence impedance because in the stationary frame and it have a more very clear physical meanings because we can see it in the stationary frame. And but some researchers also prefer use the DQ scalar impedance because it's based on our control frame. So in the control frame, it means that all the variables in the steady state is a DC component, so it's more better for doing the linearization process. Okay, so here I'm going to introduce how can we deduce it from the DQ scalar impedance to the alpha beta sequence impedance. And this is the DQ scalar impedance. We can see that it means that it's in the matrix form. The characters, I think that you should have some basic idea that of the DQ scalar impedance is that all the variables in this matrix and are the scalar variable. It means that it has no J part, imaginary part. It's just only a real part. So it's a scalar form. And it can be expressed as a UDS, UQX, and IDS, IQS. So DDD, DQ, and DQD and DQQ are all the scalar forms. And if we are dealing with a symmetric system, just as the first two models of I introduced without considering the PL effect, we can combine the dx voltage and the q-axis voltage together with a complex vector. You can see that it's a complex variable, and this is also a complex variable. And by combining this, why do we do this? Is that this can simplify the matrix to just one formula equation, like here. So it can avoid using the 2x2 matrix. And if the impedance is symmetric, we can just get the formula like this, the DDQ. If I use the border fault, it means that it's a complex variable. It contains the J part, okay? So it can be expressed in this form. And since it's symmetric, so the transformation for the DQ sequence impedance to the alpha beta sequence impedance is very simple. We can just make a frequency shift like here. And this is also can be equivalent to the A X to the phase A voltage and the phase A current impedance. So this is a very obvious impedance that we can acquire in the real cases. And the difficulties here is that we are facing is if the impedance is asymmetric, like I have introduced before, since the PL effect is considered, so we will introduce some asymmetric metrics here. So then if we are encountering the asymmetric metrics, how can we transform the DQ scatter impedance to the sequence impedance? And I think that you can find more details in this paper. It's a very good paper and it contains how can we transform the sequence domain impedance to the DQ domain impedance. And here I just make some the important equations of this paper is that we can have some transformations that if we need to transform the DQ scatter impedance to the complex impedance, it means that we also need to use two complex variables to express the dx voltage and qx voltage if it's asymmetric. Okay, this is very important. You should keep in mind. Since it's asymmetric, so you can't just use one single complex vector to express it, like in this form, like in the previous slides. In this form, you can't use one single complex vector. You need to use two complex variable. So here I just use the UP and UN represent as the positive and negative. So it means that the UD is equal to the UPS and plus UNS, and the UQS is used J terms and to times these two terms. So it means that if you are encountering a asymmetric system, you can't use only one complex variable to express this kind of asymmetric characteristics. Okay, I have put several times emphasis of this term because I think that it's a little difficult to understand this concept. So here that if we have know these characteristics, we can make a transformation like this to make all the to change the dx and qx voltage and changes the dx current and qx current by these two metrics. Then we can get the dq domain sequence model. The ups and uns are both in the dq domain, so we can get this matrix form. So for the asymmetrics, even if you are using the complex variable form, still you need to use a 2x2 matrix to represent the impedance characteristic of this kind of system. Okay. So this transformation is we are called by calculated by this, and this is the DQ sequence impedance model by using these two matrix transformation. And then is the transformation from the DQ sequence to the phase sequence model. You can see that since this is still in the rotating DQ frame, and our objective is to transfer it into the stationary frame. So here's also some tricks that you need to be careful. If we want to change the DQ sequence domain model to the alpha beta is stationary alpha beta frame, we need to notice that for the positive sequence voltage in the DQ domain, it is rotating in the clockwise. Okay, so it means it will just use the this E minus J theta. Okay, but if you are using the positive sequence, is using this EJ theta. So there is because in the rotating direction of the positive sequence and the negative sequence are different from the DQ domain to the alpha beta domain. Okay, so we can get this, and I think that if you guys have some experience of this part, you may notice there should be a EJ2 theta for you are making the transformation, and this is the reason of this EJ2 theta, because the positive sequence and the negative sequence are rotating in the different directions. Okay, so this is the maybe I need to make a stop here. So do you have any questions of this transformation? Because this is very important for the modeling and impedance transformation. Can you guys follow here? Okay. And here that, okay, so since that we are making the impedance model in that part, then we are going to do some validations of the impedance model. And how do we do the validation? That is by the frequency scan. What does the frequency scan mean is that, okay, here I think that, sorry. Here that is, we needed to inject some small signal voltage, like harmonic voltage here for into the main circuit, and then we can get the corresponding harmonic voltage by using the Fft analysis, and then we can get the harmonic impedance of this by using this equation. And this is the parameters we are using in the simulation. And this is the control parameters. And we can see that the main control parameters of the system is that the DQ current controller is a PI. Oh, sorry, this is a PL parameters here, using the here. And this current control parameter is the GCS here. And this is a control delay is used here. So based on the parameters and the main circuit parameters, we can get admittance models by using the frequency scan. We can see I think that the points are represented using the simulation results, and the curves and the dashed curves are by using the simulation by using the mathematical models. So we can see here that all the points are located in the solid lines. It means that it just corresponding very well with our mathematical models. And the dashed line is means that we didn't consider in the PL effect. We can see that it have a very obvious effect in the phase characteristics. We can see that if we are considering the PL effect, it will have some negative margin of above the 90 degrees. It means that it will have some negative resistance. But if you didn't consider it, you can't get this characteristic. So it means that for the real applications, especially when we are doing the analysis of the low frequency oscillations, we needed to consider in the PL effect. And then since we have verified the characteristics of our mathematical model, then we needed to do some stability assessment. And here, since it's a 2x2 matrix, we can't use the conventional simple Nyquist criterion. We needed to use a generalized Nyquist criterion. And here I wanted to, maybe some guys of you didn't know the concept of the generalized Nyquist criterion. So I just put it here. And what does the generalized Nyquist criterion mean? And you can see that for the impedance assessment criteria, one important thing is that we needed to do is first we needed to transfer the Dfidsc site considering the RSC also, okay, to Loudon circuit, Loudon equivalent circuit is a biocurrent source and admittance. And then for the grid side, if we are considering the grid impedance is in the Sevelen circuit, you can see here that it has a impedance and the grid voltage. So here that we can see that for the grid impedance, since it's symmetric, you only have the LG, so it will have no of diagonal elements. It only has the diagonal elements. But for the Dfidsc impedance matrix, you have the 4 elements since it's asymmetric. So we can get the current injected to the grid as this equation. And we have some assumptions for the impedance assessment used here is that if you are connecting your RC plus Dfidsc model to a strong grid, it means that the YDFIG is stable itself. It will have no stability issues if it's connected to the strong grid. So this part we can ignore. We only focus on this part, the denominator of this. If we want to guarantee the system is stable, we need to guarantee all the pores of the denominator should be on the left half plane. Yes, so basically, we can calculate the roots of these characteristic functions, but it's also is always very complicated in the real cases since it's a high order equations. So the generalized Nyquist here is used is that by we can use the determinant of this 2x2 matrix, and then we can get the 2 eigenvalues of the matrix of this for assessing the stability by checking whether the 2 eigenvalues will encircle the -1. So this is the generalized Nyquist criteria. And here I am going to make some examples of how to use the generalized Nyquist criteria. We can see that the control here I'm going to introduce the control delay effect of we can see what's the difference. And since it's a 2x2 matrix, so it has 2 eigenvalues. 2 eigenvalues is that I use number 1 and number 2 to represent the 2 eigenvalues. And we can see from this is a full view of the Nyquist criteria diagram, and this is an enlarged view of the Nyquist diagram. And here we can see is that without a delay, and it's the eigenvalues will not encircle the -1. But if you will consider the delay, it will encircle this. It will cause the instability issues. And this is one characteristic that is caused by the delay effect. And I think I will do the simulation verification in the later slides. And another characteristic we should notice here is that since the locus of the eigenvalues number 1 is always located in the right side of the eigenvalues of number 2. The number 2, which means that the number 2, so you can see here that the number 1 is this pink curve, and this number 2 is the blue curve. We make a comparison between these two eigenvalues that we always notice that for the number 1 is always in the right side of the number 2, so which can't encircle the -1. So in order to make the Nyquist diagram more simple and clear in the next Nyquist diagrams, we are only considering the number 2 in our later research analysis. Okay, you can see that we are going to make the analysis of the PL parameters. We can see that if we are increase for the blue, the KPP is equal to 0.8, KPI is equal to 8, and this red line we increase the proportional gain and the integral gain, and then for the green line we still increase it, and then we can see from the Nyquist criterion is that we will encircle the -1 with the increase of the PL parameters. And this is the simulation results. We can see that with the increase of the PL bandwidth, it will have some instability issues, and you can see the oscillations. And it tells us that the high PL bandwidth will cause instability of the Dfidsc system under the WinGrid. Okay, so that's why there are a lot of papers are talking about we shouldn't use a high PL bandwidth of the wind farm control during the WinGrid conditions. And this is one more aspect when we are considering the water speed change. Water speed change, the omega r equal to 35 Hz means is the subsynchronous rotating water speed. The omega r represents the water speed in the frequency domain. So the omega r equal to 50 Hz, it represents us in the synchronous speed, and the omega r equal to 65 Hz, it represents us in the super synchronous speed. So when we are changing the speed from the super synchronous from the 40 Hz to the 35 Hz, we can see that there will be some oscillations. We can see that this is stable with the water speed, and this is with another water speed where it has some oscillations. And we do a Fft analysis of this simulation results. You can see here that it have some oscillation frequencies. It has two frequencies because of the frequency coupling characteristics is asymmetric. So these have a 3 Hz and 103 Hz. It is just corresponding with the Nyquist criterion. So it also validates that our mathematical model of the Dfidsc system is also correct. So for this part, I want to make a short conclusion here is that when we are considering the conventional SRPL, it will indeed introduce a asymmetric matrix to the impedance, which will make the Dfidsc system more complicated. It means that the CISO method can't be used. We need to use the MIMO method to do the stability analysis. And the second is that the DQ impedance and the sequence impedance can be converted to each other, which are essentially equivalent. So for you guys, if you are encountering when you are doing some later research of using the impedance models, whether you are using the DQ domain impedance model or using the harmonic derivation under the for the sequence domain for the sequence impedance model, they are essentially equivalent. They will get the same conclusions, no doubt. Okay. So and then is the impedance results would be wrong without considering the PL effect, and which might cause a wrong stability assessment. And the last is that we can see that the generalized Nyquist criterion can be applied for the accurate stability analysis, just as I have shown to you with considering the control delay effect, the PL parameters, and the water speed changes. It'll just corresponding very well with the simulation results. But the disadvantage is that it is only based on the figure. We just see the figure and then to say the conclusions, whether it's stable or not stable. It's difficult to tell us how to design the parameters of the system, how to improve the stability systems, the stability of the system, and how to make a good parameter design of the Dfidsc systems under the WinGrid. Okay, so this is the first part. I'm just make a brief introduction of how can we model the Dfidsc systems when we are considering the PL, and how to make the stability assessment of this kind of system under the WinGrid. And in the second part is that I want to talk about how can we improve the stability of the Dfidsc system. Since this is our objective, the first part is how can we know the system characteristic under the WinGrid, the conditions. That is from the understanding perspective. First, you need to have a good understanding of this kind of system. And then is that we need to improve the stability. That is our objective of the real applications. Because in the real wind farm applications, you can't avoid the WinGrid conditions because it's always connected through long transmission lines, so it can't be avoidable. And what we need to do is how can we improve the stability of this kind of DFIG system connected to WinGrid? And in order to find the some good method for improve the stabilities, I think that I need to make a recap of the small signal of the conventional SRPL, since this is the main reason that caused the instability issues of the DFIG under the WinGrid. Because we are considering the PL, it means that the interactions between the DFIG system and the grid impedance will be more serious. Okay, so a very basic idea is that if we can disconnect the strong interaction between the DFIG and the WinGrid, it may improve the stability of the DFIG system. Okay, so that's a very intuitive ideas from this perspective. And this is a conventional SRPL. I have just shown in the former slides, and we can see that. Okay, I think that that's one perspective I just introduced is from the interaction perspective between the DFIG and the grid impedance. And the second view I want to say is that here, why the system is become complicated is because that the asymmetric characteristics of the PL. Why this PL is asymmetric? Because it makes the complex variable to a scalar variable between the relationship between the PL angle and the perturbations. You can see that first is the obtained theta PL is a real number. It is a scalar variable, and only the QX voltage is controlled without considering the DX voltage. So you can see here that the conventional is only controlling this in the Q axis without considering the DX axis. So this is called the main cause of the asymmetric characteristics. And since we are encountering the asymmetric characteristic, it will make our system more complicated. And that's the reason we can't use a very simplified CISO methods for analyzing this kind of stability issues, and can't use the conventional control theory like the board diagram or to make a parameter design. So here we can have a very basic idea is that can we make the characteristic of the SRPL to be symmetric? I think I make a stop here that you think about this. Can we make the characteristic of the PL to be symmetric? Okay, so here is that in this paper, the symmetric is proposed by Dongshen Yang. I think it's a very interesting idea here. Is that since we only control the QX voltage, that's the main reason of causing this kind of asymmetry. Okay, if we want to make it symmetric of the PL, the basic idea is that why do we just add another control loop to the DX voltage control? You can see here, I not just only control the QX voltage, I also consider controlling the DX voltage by using a GPLS and the integral. So you can see that the control loop is totally the same with the QX voltage. So this is the characteristic of the symmetric PL is that first is the obtained orientation angle is a complex variable. It's not a scalar or a real number in just as the conventional PL. You can see that the theta is equal to theta d and plus j theta q. So you have the imaginary terms, okay? And not only to control the QX voltage, but also control the DX voltage to a relative value. So then we do a small signal analysis. We can get that the input is the perturbation of the voltage, and the output is the variation of the angle, acquired orientation angle. So you can see here that we can see the relationship between the variation, the angle variation, and the perturbation of the voltage is not just a scalar form. It's not just related to the VD or single VD or single VQ. It's related to the whole complex variable. You can see this delta V, it contains VD and JVQ. So it's a vector. So it means that if we are using this kind of symmetric pair, it will make the perturbations on the stator voltage and to the angle variation will also be symmetric. It's just can still use a complex variable form. So if we can make this simplification, it means that our single input, single output analysis methods can be used for our parameter designs. Okay, so here that's if we are using this kind of symmetric pair in our control diagram, we can get the complex transfer function of the Dfidsc in the DQ frame when considering the pair. The block diagram is the same with the conventional SR pair, since the effect is also introduced by the Park transformation and the inverse Park transformation. So this whole view of the transfer function diagram is still the same, but the difference is that if we are using the symmetric pair, here we can use a very simplified complex variable, but not using a 2x2 matrix to express the relationship between the current to analyzing the effect of the Park transformation and the inverse Park transformation. So if we can use the symmetric pair, we can get the admittance of the whole system is still in a symmetric way. So if we can use this, it means that we can still get the alpha beta frame admittance by just using the frequency shift here. And the advantage of use this symmetric pair is that we have eliminate the frequency coupling effect of the system. And then we can use a single input, single output analyzing methods to do the parameter design of this kind of system. And I will show you the difference between use the conventional pair and the symmetric pair here. You can see that this is also by the same frequency scan procedure I just mentioned in the previous slides. You can see that this is the blue line shows the conventional pair and the red line shows the symmetric pair, and the points are by the simulation results. You can see that if we are trying to check the frequency coupling characteristics, we are mainly focusing on the off-diagonal metrics like Y12 and Y21. We can see that for using the conventional pair, these lines and these points are very higher than the symmetrical pair. It means that it has a strong coupling. If we are using the conventional pair, it can't be eliminated. But if we are using the symmetrical pair, you can see that the magnitude characteristic it all suppressed using this model. And do a further verification is that we injecting the same we only injecting like 350 hertz for the conventional PL. We have two current output. This is called frequency coupling. But if we are using the symmetric PL, if we just injecting one harmonic voltage, it only have only the one harmonic current. So it means that the frequency coupling is eliminated by using this kind of symmetric PL. And then since it's symmetric, so we can use the board diagrams to do the stability analysis. This is the equivalent impedance model of the whole systems. We can still use the Y11 and ZG to do the simulations. But this is a comparison between used PL and without considering the PL is that we can see that even you are using the symmetric PL, the advantage is that the frequency coupling phenomenon is eliminated. but it doesn't mean that the stability is improved. So I think that you guys should be very careful of these two concepts. These are two different concepts. Frequency coupling and the stability performance are not the same concept. It doesn't mean that you eliminate the frequency coupling can improve the stability performance. Okay, so it's different. So here is that by using the symmetric pair, you are just eliminating the frequency coupling phenomenon, but it doesn't mean that your stability margin or stability performance is improved. So here I want to say that you can see if we are didn't considering the PL effect, like the ideal grid, like in the previous slides, without considering the PL, it's only the resistance and the inductance characteristic. You can see that it's a passivity system. So if you are even you are connected to a WinGrid, it will not cause the instability issues. But if you are considering the symmetric PL, you can see that it will have some negative resistance. And that's the main reason of causing the potential instabilities under the WinGrid. Because under the WinGrid, you may have a serious compensated WinGrid. It means that you have some capacitor and inductance, and if they are encountering together and you have a negative resistance, so it will become unstable. So in order to make a verification of this kind of instability issues, I have done some simulations. You can see here that under the WinGrid, even we are using the symmetric PL, it will still have some instability issues. You can see that the oscillations, and by doing the Fft analysis, and it have some high frequency oscillations of 190 Hz here. So, but one thing very interesting you should notice here is that for this kind of oscillation, it only have one frequency. It didn't have two frequency component. Okay, what's the reason? Is that it's because we are using the symmetric PL, so it's a symmetric system. It don't have the frequency coupling phenomena. Even you have instability issues, you only have one frequency oscillations. So that's the difference between the previous instability phenomenon. It will have two coupling frequency, but here it doesn't have. So this is it means that we just solve the question of the frequency coupling issues, but then our ultimate goal is to improve the stability of the whole system. So here that I want to say is how can we improve the stabilities if we are using the symmetric PL? Because the first step is that we're using the symmetric PL to eliminate the frequency coupling. So now we can use the single input, single output method to make a more intuitive parameter design. And then this part I'm going to introduce how are we going to design the parameters to improve the system stabilities. And here we can see that from the Dfidsc impedance model based on the symmetric PL is use we have the I just have mentioned the impedance conception is that from the we need to find the relationship between the input voltage and the output current. So we need to find the relationship between these two variables, and the division of these two terms are the impedance. So we can see here that from the root to the from the voltage to the current, we have three roots. You can see that I have marked as 1, 2, 3. So it will introduce the effect from these three directions. And in order to make a more intuitive analysis, I have divided in these three terms as individual terms. I call this as from the path 1, we call this as the ZO, and from the path 2, since it's based on the current Park transformation, I call this as a DPNI. It means that from the current transformation effect, and this is the DPNU. It means that it's from the inverse Park transformation of the voltage. So you can see here that this is the whole impedance of the DFIG system. It's since these three impedances are in parallel, so it's in the parallel form. And then we make a board diagram of this impedance. We can see that this is the amplitude frequency characteristic curves of the impedance subsystems. And this we have the solid red line is the DPNI, and the DO is the without considering any other like these parts, and this is the DPNU is caused by this part, and the green dot line is the real DFIG impedance. So we can see here that there is a very obvious notification I wanted to say is that we can see that from this maybe 10 Hertz to this 200 Hertz, the admittance, the impedance is mainly determined by the DPNI. Since you can see that the DPNU is very high, and since these three impedances are in parallel, so the whole impedance is determined by the smallest impedance, okay? Because it's in parallel, so it's determined by the smallest impedance. And the smallest impedance in this parameter, you can see that why these two are marched together is because this is very small. So it tells us that if we want to make a further simplification of the impedance character, we can just use the GPNI to represent the whole DFIG impedance. So you can see here that this is the phase characteristic of this impedance. We can see that if we didn't consider the PL effect, it will not have some negative resistance characteristic. But if we consider it, you can see it have some negative resistance. So there are two main conclusions here. That is, from the 50 to 200 Hertz, the impedance is mainly determined by the DPNI, and the DPNI will introduce a negative resistance in the frequency range, and which is the main reason, and we should that might, okay, this is a type error, might cause the instability on the WinGrid. So here that I want to say, since we find the main reason is caused by this GPNI, okay, from the current transformation. If we want to increase the stability performance, and a very simple idea is that we can add another terms to the feed forward to encounter the negative effect, to counteract the negative effect of this GPNI. Okay, so if you can counteract the negative effect of GPNI, then you can eliminate the negative resistance caused by this transformation. So this is our idea. And then we add a virtual impedance, that is by adding this GPNI here. We can see that this is a transformation, and by using this impedance reshaping, we can see that the phase margin is increased a lot. And by increasing this phase margin, we have also done some experimental validations. We can see that the experimental results with the proposed control strategy, when we are increasing the PL bandwidth from 80 Hertz to the 140 Hertz, you can see that if we didn't use the impedance reshaping, it will have oscillations. But if we are using the impedance reshaping, and it will become stable. And here's that using the experimental results of with the different SCR. You can see that the former is the SCR equal to 2, and it will is stable. But if you are equal to the 1.3, it will still be stable. So it means that it will become have a very adaptive characteristic during the various SCR situations. So here that we can get is with the proposed impedance reshape method, the negative resistance can be counteracted and the stability can be improved. Furthermore, is that the frequency coupling and the system stability, I want to make an emphasis on these two different conceptions, is that these are two separate issues. And eliminating frequency coupling doesn't mean that you can improve the system stability. And if you want to improve the system stability, you need to find some other control methods to reshape the impedance of the system and to counteract the negative terms that are causing the stability problems. Okay, so the conclusion of this part is that first is the frequency coupling phenomenon of the Dfidsc system caused by the PL can be eliminated by using a symmetric PL. And then is that the sequence impedance model of the Dfidsc system can easily be obtained based on the complex transfer function, since it is a simplified single input, single output system with a symmetric PL. And last is that the seesaw impedance reshaping method can be implemented to enhance the stability of the Dfidsc system under the WinGrid conditions. And I think that if you want to find more details about these methods, you can find, you are referring to read these two papers. I think it has a very detailed formulation and writing of these two different kind of methods. Okay, I think it has been past 1 hour, so maybe